much you try, you will never grasp just how small and unassuming an atom is just too small. It is so small that even the head of a pin may contain up to 300 trillion of them. Everything around you, even you, are made up of atoms. Now imagine everything in our universe, every last atom between here and the edge of creation, unpacking it in an area so small that it does not have any dimensions. This is called a singularity, and now you're ready to start an old-fashioned, traditional Big Bang universe. The Big Bang Theory is an effort to explain what had happened at the beginning of our universe. Only during the previous century was the Big Bang Theory developed, and, as any successful theory, it has had its fair share of challenges that it has had to overcome. This video presentation will tell you the life story of the Big Bang Theory, as well as some of the main challenges that it had to overcome. The Big Bang itself is a contradiction because it was not big and there was no bang. Instead, the universe sprang into existence as a singularity 13.7 billion years ago, and it expanded rapidly rather than exploded. You may wonder, what is a singularity, and more importantly, where did it come from? To be honest, nobody knows for sure. These singularities defy our understanding of physics. Our universe is thought to have started out as an infinitely hot, infinitely dense, and infinitely small singularity. Where did it come from? How did it form? Why did it appear? Nobody knows. The Big Bang Theory was first introduced by Belgian physicist and priest called Georges Lemaitre in 1927. Nowadays, the Big Bang Theory may be the leading cosmological model of how our universe developed. However, in the 1920s it was anything but. Many famous scientists, such as Albert Einstein and Fred Hoyle, decided to condemn the Big Bang Theory. They chose to side with the eternal static universe theory instead. This states that a universe is neither expanding nor contracting. Einstein even derided Lemaitre's theory in public, saying that his math was correct, but his physics abominable. Despite the public's skepticism, the Big Bang Theory achieved its first victory in 1929, when Edwin Hubble observed the fact that most galaxies were redshifted, and therefore racing away from our own Milky Way. In addition, he knew how galaxies were not randomly dashing through the cosmos, but that their velocity depended on its distance from us. This is the Big Bang, and exactly what Lemaitre had theorized. The relationship between a galaxy's distance and velocity became known as Hubble's law, and it states that at some point in the past, all galaxies must have been on top of one another. Theoretical calculations proved that an eternal universe was not possible due to this law, and therefore, the eternal static universe was revised into the steady-state theory, which states that new matter is continuously created as the universe expands. Hubble's law was enough to convince Einstein to change his view about the Big Bang Theory, yet many scientists continued to believe in the steady-state theory. The main criticisms were that the Big Bang model implied that the stars were younger than the universe itself, and why were light atoms more common than heavy atoms? Supporters of the steady-state universe could not give any clear answers either, yet they retained that the universe always was this way, and always would. This answer was far from satisfactory, but at least it was consistent. It was important for the Big Bang supporters to find more evidence and answer these questions, if they wanted to sway the opinion of many scientists in their favor. One of the main problems that the Big Bang faced was that Hubble's measurements implied that the universe is just 1.8 billion years old, while the land even on Earth is clearly older than that. This age paradox would become known as the timescale difficulty, and the only prospect of resolving this paradox would be finding an error in Hubble's measurements. Luckily, for the Big Bang supporters, this was just the case, when a German immigrant named Walter Bade discovered that there are two different types of stellar populations, and variable stars. Due to these realizations, the assumed scaling of the universe was double, and therefore, the universe was now 2 times older. However, this answer was still far from satisfactory. It would be Bade's own student, Alan Sandage, who would revise his master's measurements. Using improved photography techniques, Standage was able to tell that the perceived bright star in any distant galaxy was not a star at all, but rather an H2 region, which is a vast, hot, light-absorbing cloud which can outshine any star. Basically, this meant that the brightest star in the distant galaxy was actually much fainter than initially thought. So therefore these galaxies were much farther away. Standage measured the distance of many galaxies and found out that many were 10 times further away than Hubble thought. So the Big Bang Theory was able to overcome the timescale difficulty after all, and no longer could the supporters of the steady-state theory mock the Big Bang for it. Still, problems pursued the Big Bang Theory, such as how the heavier atoms were created. Ironically, it would be Fred Hoyle, an avid supporter of the steady-state theory, who would answer this puzzle in the 1940s. Stars are in a state of equilibrium, with the gravitational pressure pushing a star in on itself, but with the heat that it creates pushing it outwards. However, once a star reaches its twilight years, it will start losing heat, and therefore gravity will prevail, pushing the star in on itself. A star's death is not as simple as this, however, as this increased gravity will cause the stellar core to heat up, which places the star in a state of equilibrium again. This happens many more times to a star before it dies. This stop-start collapse causes a star to endure a hot, lingering death. Hoyle would analyze the deaths of various stars, and after years of careful measuring, he completed the various temperatures and pressure changes that a star endures as it reaches the end of its life. Crucially, he worked out how these extreme pressures and temperatures may lead to the creation of medium and heavy atoms. Both the Big Bang and the steady-state models cannot explain the creation of heavier atoms. However, only the Big Bang was able to explain the abundance of light material satisfactorily. This explanation was a big win for the Big Bang, yet it would have not been possible without the immense contribution of the avid steady-state supporter, Fred Hoyle. In addition, the Big Bang model would soon receive another boost when telecommunications giant AT&T hired Carl Yansky, a 22-year-old from the University of Wisconsin, to inspect the constant cackling noise during phone calls in 1927. Yansky built a giant and highly sensitive radio antenna at AT&T's legendary Bell Laboratories to find out what was causing this constant hiss. After laboriously pointing the antenna at every direction in the sky for a few months, it dawned on him that the interfering noise was a constant hiss of an origin that was not yet known. Yansky spent several months analyzing this unknown radio source, and he soon found out that it peaked every 23 hours and 56 minutes. He took this time interval problem to Marvin Skillet, an astronomy expert, who was able to point out the significance of the 4 missed minutes. His calculations proved that the constant hiss was coming from a consistent place in the universe, but beyond the Earth and our solar system. Over the next year, a group of scientists at Mount Wilson Observatory concluded that the radio signals came from radio galaxies. The distribution of these radio galaxies throughout the universe would become crucial to the Big Bang versus steady-state theory debate, as the Big Bang model implies that these young galaxies will only be in the far reaches of space, while the steady-state theory states that these galaxies would be evenly spread out, with some being close and others being far. In 1961, a scientist named Edward Royal collected the position and data of over 5,000 galaxies. He concluded that these radio galaxies were indeed far away, teetering at the edge of the universe. The Big Bang model was right after all. However, the main victory for the Big Bang came in 1948, when Russian-born scientist George Gamow produced an important cosmogony paper with his student, Ralph Alpher. This paper was called The Origin of Chemical Elements, and it predicted the existence of cosmic microwave background radiation, or CMB radiation for short. Gamow and Alpher deduced that it would take the universe 300,000 years to turn the plasma that was occupying the universe at the time into atoms. This event is known as recombination, and after this event, light could travel unhindered. Gamow and Alpha deduced that this sudden sea of light must have left a luminous echo, and Gamow and Alpha hypothesized that the universe should be full of this microwave light and that it should be coming from every place in the universe. However, many astronomers and scientists did not make any effort to detect this radiation, mostly due to a pure lack of interest and the fact that not much was known about microwave radiation at the time. Consequently, their prediction was not substantiated until 1964, when Arno Penzias and Robert Wilson discovered CMB radiation by accident, while experimenting with the Holmdel-Horn antenna. After the Big Bang's introduction nearly a century ago, what has become of it? Well, many questions remain unanswered. It has withstood the criticism of many competing theories. As a result, nearly all cosmologists now back the Big Bang Theory. To answer its shortcomings, the steady-state theory was revised into the quasi-state theory, but to no avail, as the shift towards the Big Bang Theory was now complete.